Hello! Glad to start with you day 38. It seems that I'm progressing quite well. So I'm just going to bring my phone to set up the topic. So let's start with the first hour. Good luck!
You're the man. You're going to math jail. It's a wonderful place. All right. I'm glad you Okay, let's see what happens here. So we know we have a substitution. That's why the second sentence is even there, to give us some numbers to allow us to solve for k. So when we're dealing with direct or even inverse variation in just a little while, we're going to have one of these equations, either y equals k times x, or in the future y equals k over x. So the problem is going to give you two numbers to plug in. Since we have those three variables up there, they have to give you two of them to solve for the missing one. In our case, they give us y, which is 20. Do we know what x equals? I'm sorry, k. Do we know what k equals? No, not so much. We do know what x equals. That's going to be 15. How are we going to solve for k in our problem here? Sure. By what? Okay. So, of course, our 15s on the right-hand side, they create that 1 for us, and we're left with k. On the left-hand side, what are we going to have? Yeah, good. So we're reducing this as well. Are we done? No. We're almost done. We've done the hard part. We've solved for k. However, what I told you last time is that we want to rewrite the equation because that's going to allow us to solve for any other pieces of information that we might need to find. So tell me exactly what I need to have once I resubstitute in k. What am I going to get now? Good. So essentially, we're just changing this by replacing k with what we know k to be. Would you raise your hand if you're okay with this direct variation? Would you like to see how this is applied to like a real life situation? So, nah, not so much. By the way, the answer to that question is always, yes, Mr. Leonard. We're so excited to see. That's the answer. So are you guys ready to see how this is going to be applied to this? Oh, good. We're so excited now, and the rest of it, we're so excited. Okay, good. I'm sure you are. Okay, so let's suppose we had this situation. From the ceiling, I'm going to hang a spring. Okay, so like a scale, basically. So some sort of spring from the ceiling. And I'm going to put some weight on the spring. What's going to happen to the spring? It's not going to go up, is it? It's going to go probably stretch down a little bit. Let's say that I take that weight off and I put a heavier weight on. What's going to happen to that spring? It's going to go even more. So would you agree that for a certain stretch of the spring, now eventually that spring is going to stretch all the way to its maximum and not go any further, right? But for a certain distance, the more weight we put on that spring, the more it's going to stretch. Do you agree? Does that fall into the category of direct variation? More weight equals more stretch. So those things are tied together. Less weight means less stretch. So we know that as the weight goes up, the stretch goes up. Let's see if we can write out a word problem, identify that it's direct variation, see if we can solve some things about it. So let's suppose that the distance a spring stretches, that's going to be a tongue twister the whole day. The distance a spring stretches is directly proportional to the weight that's attached to it. Wait a minute, directly proportional? What's that mean? What's directly proportional mean? What's the key word in directly proportional? Directly. That's it. It's the same thing as varies directly. So that's a different way to say it, varies directly or directly proportional. It's the key word is really direct in this case, okay? So even if you see directly proportional, we mean varies directly. So the distance a spring stretches is directly proportional to the weight attached. That tells you what equation you're going to set up. Okay, the second sentence is going to tell you some numbers to plug in. The third sentence is going to tell you what to do with those numbers. So right now I'm going to take a break. I'll write more of this problem out in just a second. But I want to make sure we're understanding how to set up the equation in this case. Now, I told you last time, within the 5 minutes we really talked about this, that we don't always have to have y and x. Y and x are kind of some dummy variables. The idea is, if y varies directly as x, y comes first and x comes second. In our case over here, the distance the spring stretches is directly proportional to the weight attached. I don't have an x and a y. What are my two variables that I'm talking about here? The distance the spring is stretching, that's great. So this is one of them. And what's it proportional or directly proportional to? So weight's another one. So maybe we don't have y and x, maybe we have, what variables do you want to use? Yeah, original, right? D for distance and w for weight. So how are we going to write out the equation if we don't have y and x anymore, we have d and w? Can you tell me? Sure. Y, ladies and gentlemen, is that d equals k times. What's that k times coming from? What word clues you into that? Good. Okay. So d for our distance, that's the first thing that we saw in our sentence. So distance is very directly. That means distance equals k times, well, whatever weight we're going to put on that thing. So that's our first part to our problem here. We need to identify that equation we're working with. Now I'm going to fill in the rest of our, I'm going to move this down a little bit also, fill in the rest of our question. So d equals k times w. We got that from our very first sentence. Then it has to give you some information. Let's say a 56-pound weight on this spring stretches at 8 inches. 72 miles an hour because I don't want to get tickets. Example, then do a work problem similar to this one, and we'll be done with it. The hard part, we've solved for K. However, what I told you, what word clues you into that?
Right.
Good, okay, so D for distance, that's the first thing that we saw in our sentence. So distance is very directly, that means distance equals K times, well, whatever weight we're going to put on that thing. So that's our first part to our problem here. We need to identify that equation we're working with. Now I'm going to fill in the rest of our, I'm going to move this down a little bit also, fill in the rest of our question. So D equals K times W. We got that from our very first sentence. Then it has to give you some information. Let's say a 56-pound weight on this spring stretches at 8 inches. Well, that tells you some pretty good information. Can you please tell me where's the 56 going to go in the equation we just made up? Yeah, why? Okay. And where's 8 going to go? So we could actually substitute our 56 and our 8 for the equation we just made up. If a 56-pound weight stretches that thing 8 inches, the distance it's stretching is, well, it's 8. We don't know what K is. That's really part of this problem, times 56. I'd like to see if you understand what we're talking about here. Not sure if you're okay getting from this point to this point. Yes. Good, okay. What do we need to do to solve for K? 8 or 56? Where your k's at, when you get k by itself, what's attached to the k? Okay, so we're divided by 56 in our case. Wait a second. 8 over 56, is that even possible? It's not going to be a whole number. That's fine. We don't have to have a whole number over here. What is 8 over 56? Sure, we're going to simplify that fraction. We're going to get 1/7. There's nothing that says k has to be integer or a whole number. What it says is that k is being multiplied by x if it's directly proportional or very directly. So in our case, we get 1/7 k equals k. 1/7 equals k. Okay, we should be good at this point. What do we do now? All right. So when we do that, the d is not going to change. I know all that's changing is that k. So d equals, instead of k, I'll do the 1/7. That's what we just found, times w. Now, this allows you to solve for any other piece of information I want. So if I say, instead of a 56-pound weight, I want you to go ahead and put on, what do I have down here? An 85-pound weight. Could you figure out how much that stretches? What are you going to plug the 85 into? That's the new weight. So the idea is this. We use our first sentence, or the thing that says very directly or directly proportional, or in the future inversely proportional or varies inversely, to set up our equation. The next sentence is going to give us two pieces of information. That lets you solve for your k. Once you solve for your k, that's setting you up with a very nice equation you can use to solve for any other piece of information. So when I do this next part, how far will an 85-pound weight stretch this spring? We can figure that out. And by the way, just one more time, where's the 85 go? Does the 85 go for the D or for the W? Yeah, it's definitely a weight, so let's plug that in. I have D equals 1/7 times our 85. 1/7 times 85, well, 1/7 doesn't really, or 7 really doesn't divide the 85 evenly, does it? Okay. So we can write the distance equals 85 over 7. 85 over 7 what, though? What are we talking about here? So make sure we're using our units correctly. This isn't stretching feet or anything, right? It's definitely not stretching miles. It's stretching inches. 85 over 7 inches, or if you want to use your calculator to get a decimal, because typically you're not going to go, oh yeah, I just traveled 85 over 7 inches. Do you do that? I'm traveling 85 over 13 miles per hour, officer. That's how fast I was going, honestly. That doesn't make sense. So maybe you can translate this into a decimal for a real life situation. Do you have that now? Okay. So it's stretched at 12.14 inches. Yeah, one more question. If I did this another way, let's say I asked you, what weight would it take to stretch the spring 15 inches? Could you do that? Where would you plug in the 15? And then we just multiply by 7 on both sides, and that would give us the weight that we would need to solve or to find a certain distance of stretch. Would you raise your hand if you're okay with this problem? Setting up the direct variation. Okay, good stuff. We got direct variation. Direct means as one thing goes up, another thing goes up. As the weight goes up, the stretch goes up. There is another type of variation we have to talk about, though. Specifically, we're going to talk about inverse variation. Hey, what do you suppose inverse variation means, since we just talked about direct variation? The opposite. Yeah, it's the opposite. If one thing goes up, the other thing goes down. For instance, this always happens to me. Well, it doesn't always happen to me, but most of the time this happens to me. If I spend more time in a casino, I have less what? Yeah, I have way less money and actually have less fun too because I have less money. So the more time you spend there, the less money you have, right? The farther or the longer you drive your car, the less gas you have. Does that make sense? So as one thing goes up, another thing goes down. Give me an example of inverse variation. Can you think of one?
More you go shopping, less money.
Yeah, that's true too. Well, unless you just don't take your credit cards with you, which sometimes I do that. It's kind of fun to look, right? New shoes or something. I don't know. Actually, I don't buy new shoes. Never mind, doesn't really matter. I go car shopping. I love shopping for cars. Just drive around, free trip around the city. Like, sometimes they let you stop off and get Slurpee sometimes. If they really want to make the sale, they'll let you do that. Give a different example of inverse variation. One thing goes up, another thing goes down.
Maybe your electricity, the more you have to pay.
Yeah, it'd be direct, right? The longer you leave it on, the more you have to pay. Okay, so we have another direct. Anybody else have just? Very good. Okay, so the more you exercise, the less weight you have, unless you're just pumping iron, right? Daniel, he's getting seriously buff in there. But yeah, the more you exercise, typically maybe less fat you have, the less you're gonna have that on your body. So they're very good examples of inverse variation. Here's the idea. With inverse variation, or in other words, we'll use some variables here. If y varies inversely as x, so the key word for us in this context is inversely. If y varies inversely as x, then y goes down as x goes up. And this is the opposite of direct. X went up and y went up. In this case, x goes down and y goes up. Or x goes up and y goes down. It's that relationship. The way we can get from direct to inverse, if direct was k times something, k times, as this thing goes up, we're multiplying it by some multiplier, it's making a larger quantity, it's making this quantity larger. In order to raise a number and have something else go down, that's going to represent a fraction, because as you make a denominator larger, the value of that number drops. Does that make sense to you? So if I took the number 5, if I divided it by 7, that's probably a bad example. Let's say 35. If I divide that by 7, we're going to get 5, right? If I divide that by 10, we're going to get 3.5. Does that make sense? If I divide it by 35, I'm going to get 1. If I keep going, if I divide it by 70, I get 1/2. So as this number grows, this quantity becomes smaller. Do you see that the idea there? So this idea of this division, this is what inversely proportional is all about. It says if y is going down as x is going up, really what we have is y varies inversely, or y equals k, not times. Times would be the direct. Times means as we're multiplying, it's going to go higher. K over. This is what I talked about yesterday, making sure we knew that direct was k times, because now for inverse, we're going to have k over. So when you see the word direct, we mean k times. When we say the word inverse, we mean k over. And this is the reason why. As x is getting larger, this k, that's a constant again. Constant variation, that's not changing. This quantity altogether will get smaller, just like this example I showed you. So again, k is a constant. That's not changing. See if we can wrap this around an example, then do a word problem similar to this one, and we'll be done with our section here today. Okay, so let's suppose y varies inversely as x. Suppose y varies inversely as x. Right now, we know that that's telling us which equation to use. It's either going to be k times or k over, depending on whether we're direct or we're inverse. In our case, are we direct or inverse? So are we k times, ladies and gentlemen, or k over? Definitely. Okay, now I'm going to fill out the rest of this. Y is 6 when x is 3. Well, that's going to be important just a bit. what we're going to try to do is find k and again set up the equation. Define k and write the inverse variation equation. So read through a problem one more time. Suppose y varies inversely as x. We're not dealing with direct right now. We're not k times. We're going to be k over. We just talked about that. So when we set up our problem, which letter is going to come first in our case, y or x? Y, yeah, that's right. Because when we're looking at this direct and inverse variation, whatever's varying directly or varying inversely as the other thing, that comes first. So if y is varying inversely as x, the y comes first in our equation. It says y equals, and then we have to realize that inversely means, well, that's k over. So we're going to y equals k over x. This really says the same thing as y varies inversely as x. That's all it means. What do we do now? Yeah, same thing we just did, right? Same exact thing. So when we plug these in or substitute them in, how much is y for us? Which is 6. So 6 doesn't change. How about the k? Do we change the k right now? No, that's what we're really looking for. So k stays there, and over, oh boy, how do we solve for that? Good, yeah. This is k divided by 3, right? How do you get rid of divided by 3? What's the inverse operation here? Let's multiply. As long as you're doing it on both sides, you can do almost anything to an equation. So we're going to choose to multiply by 3. Or if you really want to think about it like this, you're multiplying by 3 over 1, right? Multiplying fractions like that. That means you can simplify them as you go. And on the left-hand side, we'll multiply by 3. So what's k equal to then? Sure. Yeah, we'll do the 3 times the 6. We'll get, these 3's are gone, leaving us with the k. That's what we wanted to have happen there. 18 equals k. Equals 18. Are we going to stop there? We're almost done. One little step. What do we do now? Okay, good. So writing the equation simply means that you're going to look back at the first equation you've written and just substitute that k, the value of k, in for k. So in our problem here, we should have y equals, instead of k, we're going to have the 18. We're still going to have x. Let's go one step further. If I asked you to find y when x is 2, could you do it? Yeah, sure. The problem's in your homework, we're going to ask you for that. Say, okay, great, you made this up. Now find y when x is 2. How much would y be when x is 2? Yeah, good, it'd be 9. 18 divided by 2, you get 9 out of that. Or find y when x is like 7. Well, then you're going to get a decimal, or you're going to leave it as a fraction. No problem. As long as we're understanding that we made this up first, and then we use this with any information I give you to solve the problem. That's really the idea. And this is going to translate to the next problem we do, which is a word problem. Okay. Let's say you're driving down the road, right? You guys ever drive? You know, okay, good. So we all have this in common. We're all drivers. Which is scary sharing the road with some of you. You gotta be honest. I don't ever see any of you, but I had a student one time. I swear every day I would go to school. I'd be driving along. I'd drive my 72 miles an hour because I don't want to get tickets. Put on cruise control. You know, have a nice day. Every single day, she'd go, wham! And she would pass me like upload. Right? She was in this big SUV. It was like an Escalade or something, and I could feel like the rumble coming, and she would just pass me. And she'd get to school, obviously, just like Tuesday. I think she had a class before the class I taught her. So she'd get here a little bit before me to go to her class, and I'd spend my hour going here and going to class, and I'd see her, and I'd always give her a hard time about it. But the point is that we went the same distance, right? We went the same distance. Who did it take longer to get here? We came from the same spot, by the way. She lived right down the street from me. So we lived like maybe a quarter of a mile away, and we came to the same exact spot. Who did it take longer to get here near her? Of course, why? I was going slower, yeah, I was going above the speed. Okay, you need to know the speed limit's not actually 72, man. Okay, so yeah, it took me, of course it took me longer than limited is how fast my car can go, obviously. So it took me longer to get here because I was going slower, or it took her shorter to get here because she was going faster. Does that make sense? In other words, the time it takes you to get somewhere is inversely proportional to the speed in which you're going. Right? So the faster you're going, the shorter it's going to take to get there, or the slower you're going, the longer it's going to take to get there. That's an inverse variation problem right there. So we're going to say this: the speed needed to travel a certain distance is inversely proportional to the time the distance can be driven. Or inversely that time. So the speed needed to travel a certain distance. So the distance is not something that's changing here. We're going the same distance. Me and the student of mine, we're going the same exact distance. The speed needed to travel a certain distance is inversely proportional to the time. So, 'Is that inversely proportional throwing you off, or is that okay with you? Just like directly proportional and very directly the same thing, very inversely proportional, same thing. Speed gives out a certain distance is inversely proportional to the time. Let's say this: the distance can be driven in 5 hours at a rate of 24 miles an hour. Really slow. Let's make it faster than that. Let's make it like 7. At 70 miles an hour. That's it. Let's see how fast you would have to go to make the same trip in 4 hours. So this big SUV is like an Escalade or something, and it crashes like that. That decimal, we're going to be. When we plug these in or substitute them in, how much is y for us? So 6 doesn't change. How about the k? Do we change the k right now? No, that's what we're really looking for. I'm going to get 1. If I keep going, hey, what do you suppose inverse variation means? The more you exercise. So the key word for us in this context is inversely. The way we can get from direct to inverse, if direct was k times something, k times, as this thing goes up, we'll multiply it by some multiplier, it's making a larger quantity, it's making this quantity larger. In order to raise a number and have something else go down, that's going to represent a fraction, because as you make a denominator larger, the value of that number drops. Does that make sense to you? So if I took the number 5, if I divided it by 7, that's probably a bad example. Let's say 35. If I divide that by 7, we're going to get 5, right? If I divide that by 10, we're going to get 3.5. Does that make sense? If I divide it by 35, I'm going to get 1. If I keep going, if I divide it by 70, I get 1/2. So as this number grows, this quantity becomes smaller. Do you see that the idea there? So this idea of this division, this is what inversely proportional is all about. It says if y is going down as x is going up, really what we have is y varies inversely, or y equals k, not times. Times would be the direct. Times means as we're multiplying, it's going to go higher. K over. This is what I talked about yesterday, making sure we knew that direct was k times, because now for inverse, we're going to have k over. So when you see the word direct, we mean k times. When we say the word inverse, we mean k over. And this is the reason why. As x is getting larger, this k, that's a constant again. Constant variation, that's not changing. This quantity altogether will get smaller, just like this example I showed you. So again, k is a constant. That's not changing. See if we can wrap this around an example, then do a word problem similar to this one, and we'll be done with our section here today. Okay, so let's suppose y varies inversely as x. Suppose y varies inversely as x. Right now, we know that that's telling us which equation to use. It's either going to be k times or k over, depending on whether we're direct or we're inverse. In our case, are we direct or inverse? So are we k times, ladies and gentlemen, or k over? Definitely. Okay, now we're going to fill out the rest of this. Y is 6 when x is 3. Well, that's going to be important in just a bit. What we're going to try to do is find k and again set up the equation. So find k and write the inverse variation equation. So read through a problem one more time. Suppose y varies inversely as x. We're not dealing with direct right now. We're not k times. We're going to be k over. We just talked about that. So when we set up our problem, which letter is going to come first in our case, y or x? Y, yeah, that's right. Because when we're looking at this direct and inverse variation, whatever's varying directly or varying inversely as the other thing, that comes first. So if y is varying inversely as x, the y comes first in our equation. It says y equals, and then we have to realize that inversely means, well, that's k over. So we're going to y equals k over x. This really says the same thing as y varies inversely as x. That's all it means. What do we do now? Yeah, same thing we just did, right? The same exact thing. So when we plug these in or substitute them in, how much is y for us? So 6 doesn't change. How about the k? Do we change the k right now? No, that's what we're really looking for. So k stays there, and over, oh boy, how do we solve for that? Good, yeah. This is k divided by 3, right? How do you get rid of divided by 3? What's the inverse operation here? Let's multiply. As long as you're doing it on both sides, you can do almost anything to an equation. So we're going to choose to multiply by 3. Or if you really want to think about it like this, you're multiplying by 3 over 1, right? Multiplying fractions like that. That means you can simplify them as you go. And on the left-hand side, we'll multiply by 3. So what's k equal to then? Okay. Sure. Yeah, we'll do the 3 times the 6. We'll get, these 3's are gone, leaving us with the k. That's what we wanted to have happen there. 18 equals k. K equals 18. Are we going to stop there? We're almost done. One little step. What do we do now? Okay, good. So writing an equation simply means you're going to look back at the first equation you've written and just substitute that k, the value of k, in for k. So in our problem here, we should have y equals, instead of k, we're going to have 18. we're still going to have x. Let's go one step further. If I asked you to find y when x is 2, could you do it? Yeah, sure. The problem's in your... Oh, we're going to ask you for that. Say, okay, great, you made this up. Now find y when x is 2. How much would y be when x is 2? Yeah, good. 18 divided by 2, you get 9 out of that. Or find y when x is like 7. Well, then you're going to get a decimal, or you're going to leave it as a fraction. No problem. As long as we're understanding that we make this up first, and then we use this with any information I give you to solve the problem. That's really the idea. And this is going to translate to the next problem we do, which is a word problem. Okay. Let's say you're driving down the road, right? You guys ever drive? You don't drive. Okay, good. So we all have this in common. We're all drivers. Which is scary sharing the road with some of you. You got to be honest. I don't ever see any of you, but I had a student one time. I swear every day I would go to school. I'd be driving along. I'd drive my 72 miles an hour because I don't want to get tickets. Put on cruise control. You know, have a nice day. Every single day, she'd go wham, and she would pass me like upload. And she was in this big SUV. It was like an Escalade or something, and I could feel like the rumble coming, and she would just pass me. And she'd get to school, obviously, just like Tuesday. I think she had a class before the class I taught her. So she'd get here a little bit before me to go to her class, and I'd spend my hour going here and going to class, and I'd see her, and I always give her a hard time about it. But the point is that we went the same distance, right? We went the same distance. Who did it take longer to get here? We came from the same spot, by the way. She lived right down the street from me. So we lived like maybe a quarter of a mile away, and we came to the same exact spot. Who did it take longer to get here near her? Of course. Why? I was going slower. Yeah, I was going above the speed. Okay, you need to know that the speed limit's not actually 72, man. Okay, so yeah, it took me. Of course, it took me long. The limit is how fast my car can go, obviously. So it took me longer to get here because I was going slower, or it took her shorter to get here because she was going faster. Does that make sense? In other words, the time is proportional to the speed in which you're going. So the faster you're going, the shorter it's going to take to get there, or the slower you're going, the longer it's going to take to get there. That's an inverse variation problem right there. So we're going to say this: the speed needed to travel a certain distance is inversely proportional to the time the distance can be driven. Or inversely that time. So speed needed to travel a certain distance. So the distance is not something that's changing here. We're going the same distance. Me and the student of mine, we're going the same exact distance. The speed needed to travel a certain distance is inversely proportional to the time. inversely proportional throwing you off, or is that okay with you? Just like directly proportional and very directly the same thing. Very inversely proportional, same thing. Speed needed to travel a certain distance is inversely proportional to the time. Let's say this. The distance can be driven in 5 hours at a rate of 24 miles an hour. That's really slow. Let's make it faster than that. Let's make it like 70. 5 hours at 70 miles an hour. That's it. Let's see how fast you would have to go to make the same trip in 4 hours. That'd go significantly faster. So you're like, okay, I usually drive down to LA, it takes me 5 hours to get there if I go 70. Now let's say I need to make it down there in 4 hours. How fast am I have to push my car? How many tickets am I going to get, basically? So how fast do you have to go to make the same trip in 4 hours? Well, guess what? This problem is exactly the same as this problem. Same thing. It's only we don't have y and x. I haven't said that. I told you something else. It is a word problem, sure, but it's kind of in a nice format. It says something very somehow as something else. It's going to be something, in this case, what's that's varying? And it's varying how? I'm sorry, varying how? Inversely or directly? Varies inversely according to what? Yeah, speed. Inversely proportional to the time. So instead of y and x, we have speed and time. We're not going to do the distance because the distance isn't changing. That was just part of the problem that says you're going a certain distance, all right? The speed needed to travel a certain distance. The speed is inversely proportional to the time. Let's set up our equation first. So first thing we got to have is either varies directly or varies inversely, depending on what it says here. Now, of course, we just talked about this is inversely. So can you tell me what equation I'm going to have? Is it k times or k over? Which one? Great. So tell me what I should write. Perfect. Do you have some numbers you can plug into that? Yeah, of course, right? The second sentence has to give you something. Does it give you a speed? What's your speed? What's your k? Okay, k is k, we don't know. What's our time? So speed was 70, k, that's what we're looking for, and time was 5. Can you solve for k in this case? Yeah, let's do that. So just like before, we'll multiply both sides by whatever's on our denominator here. We learned how to simplify those fractions a while back. K equals what now? Perfect. 350. Are we done? Are we going to have to travel 350 miles an hour to make it there in 4 hours? No, probably not. We've just kind of set up our problem now. We just managed to find K. What are we going to do with that K, ladies and gentlemen? Okay, so what's the next thing I should write, please? Okay. Perfect. So I'm just taking that K. Oops, I wrote it right. I'm just taking that K and substituting that into my original inversely proportional or varies inversely equation. The next thing you do, you look to answer that final question. How fast must you go to make the same trip in 4 hours? So the question is, where's the 4 go? Yeah, notice how you have to do this before you answer that question. You've got to have this down, right, somewhere. That way you can plug something into it to solve it. So, I'm sorry, where'd the 4 go? Yeah. It's not a speed, right? It's a time. So the speed you need is 350 divided by 4. What is 350 divided by 4? Oh, you're good. 87.5 what? Yeah, it's not a radio station, right? This is miles per hour. And remember, that's an average speed. So chances are, if you hit traffic, you're going to have to go even faster sooner. You can really push your car. Isn't this fun? How we're talking about speeding and stuff? Yeah, don't do that, by the way. I don't want you to get in jail, like sued for telling you to go 87.5 miles an hour, okay? But that's how fast you would have to go to make that same trip in an hour or less time. So in 4 hours versus 5. One other thing, if I said now, instead of how fast must you go to make the same trip in 4 hours, if I asked you this, let's say now you're going 90 miles per hour. Could I ask you how long it's going to take you? I could. Now notice this is going to be your variable. You would have to multiply by t on both sides and then divide by your speed. So you could also do that as, I think, an exercise we leave to you for your homework. How many people understood what we talked about today? Feel okay with this? Good. So directly k times, inversely k over. We set up our problems, we make our equation, and then we use that to solve.
Wondershare Filmora is a user-friendly, easy-to-use video editing software.
All right. So let's get started on 9.1. Again, we're going to be talking about something called compound inequalities. somewhere in your math career, you talked about inequalities. And those are those things that weren't equations. They had either a less than, greater than, less or equal to, or greater than or equal to. They said these numbers aren't necessarily equal. One might be bigger than the other one, but we can still make statements about them. That's what an inequality is. It's the alligator mouth that you guys were taught a long time ago with the little teeth, and it eats the bigger number. Chomp, chomp, chomp. That's usually the way it goes. A compound inequality says this. What we're going to do now is mash two inequalities together in one statement. That's the compound part of this. So while you have dealt with this part, you've never dealt with this part. So compound inequality means two inequalities joined by one of these two words, either and or. And we're going to talk about the difference between those today. So compound inequalities, that's two inequalities joined by the words and or. We're going to look at the and inequality first, kind of discover what that means, do some problems about it. Then we'll look at or, and these two are going to lead us all the way through our whole entire chapter. We're going to begin with our compound inequalities and or. So let's look at and. When you say and, usually in English, what you mean is something in combination with something else, right? And you want them at the same time. If you want to wear shoes and socks, that doesn't mean you're going to put on either shoes or socks. Socks, right? You're going to wear probably both shoes and socks at the same time. Does that make sense? And that's what and means in mathematics. It means you have one and the other occurring at the same time. In other words, it's an intersection of two sets. It's where two sets cross over. At the same time, what do they have in common? Does this make sense to you? That's what and means. It's an intersection. So we're going to talk about and as the intersection of two sets. So the intersection, this comes from the Venn diagram, which I'm going to show you in a second. Hopefully you've seen a Venn diagram. But the intersection simply means if you're going to intersect two sets, what's in common to both? Of them. So this is the commonalities or the elements that are common to both sets. That's what is included in this intersection. And we use a funny symbol for this. When you're talking about the intersection, we use kind of, it looks almost like an upside down lowercase letter n, except it doesn't have a little tail on it. It looks like this. Funny little n. It's larger than an n though. It's the intersection of two sets. You can think of it as intersection, right? So you use a little part. Doesn't that make sense? Awesome. Good joke at Monday at 7:08 in the morning. You're not waking up to laugh yet, but that was pretty funny. You'll laugh later when you watch this again. So the intersection, you think of intersection. It's the combination of both sets. If you've ever seen a Venn diagram, you know those are those circle things, right? Look like Olympic rings. There's only like 2 of them, maybe 3 of them. If we call this like our set A, whatever that happens to be, and this is our set B, can you see the intersection? Yeah, that's why we call it the intersection. That's pretty clear to see. This right here, if you're thinking about a Venn diagram, that would be the intersection of these two sets. This is all the elements of A, this is all the elements of B, whatever they happen to be. This is just the ones that would be common to A, just the ones that are common to B. This is the ones that are common to both. That's the A ones and the B ones. So that would be considered the intersection of A and B. It's elements that happen to be in both sets at the same time. And the way we write this is A intersect B. That's the way you write the intersection of two sets. To represent, you're talking about the elements common to both of them. Let's do a few quick examples just to get an idea of this. I'll show you how it's applied to inequalities, then we'll move on to the OR word. So a real easy example, well, maybe not easy example, but one that's going to illustrate what an intersection actually means is, let's find the intersection of these two explicitly written sets. In set notation, you see these symbols, these brackets, these funny ones that are kind of hard to draw if you don't have a master's degree in mathematics, but you'll get used to it. You draw like an S and then a reverse S, typically, is how you draw that. So our intersection here, I was joking about the master's degree, no, seriously, you can draw that. It's something like that. Just don't get into something like that, right? That's really not what we're talking about. It looks just kind of silly. Try to give me a nice looking bracket. Makes your papers prettier. So let's say our first set is 1, 2, 3, 4, 5. I'll finish that off. And what I'd like to do is find an intersection with this set. And their intersection will be another set. So what we're looking for in the intersection of these two sets are what numbers that are in common to both of them, or happen at the same time in both of these sets that we're talking about. So the first set, 1, 2, 3, 4, 5. The next set, 3, 4, 5, 6. What numbers are common to both? That's essentially what the intersection question asks. What numbers are common to both? Is 1 common to both? How about 2? How about 3? 4? 5? Okay, number 3? 4, 5. We already answered that. How about 6? So we're going to write the ones that just happen in both places over in this next one. What were those numbers again? Yeah, that's it. That's what an intersection is. It's just the ones that happen in both of them. Let's see if we can wrap this up just a little bit. This was pretty basic, just to get you an idea of an intersection. Let's see if we can answer some other questions. Let's say A is this set. I hope you remember this notation from the days of our domain, like a while back. Remember that? What's it stand for? How's it read? Yeah, good. X such that X, and then I give you directions about this thing. X such that X is an odd integer or odd number, and X is less than 10. That's a set A. Set B is just simply 1, 2, 3, 4. Can you give me an example? I want you to think of this. Give me an example of numbers in set A. Can you give me one example of numbers in set A? X is an odd integer, odd number, and X is less than. 10. Give me a number. 7 is a number. I heard 7. What's another one? 5 is a number. Great. How about 6? Why is 6 not in this? Okay, how about 11? Why not? Good. How about any negative numbers? No, so this is really just talking about what numbers here. List them out for me. What's the first number in this set? And then?
5, 7.
That's it. Those are the numbers. In that set. You just need to be able to identify that, right? Odd numbers are 1, 3, 5, 7, 9, 11, 13, 15, 16, that sort of thing. We're just talking about those numbers that are less than 10. So we're talking about 1, 3, 5, 7, and 9. The set B is just 1, 2, 3, 4. Tell me what numbers these have in common. Can you tell me that? 2 and 4? No, they're not odd. They are all less than 10, but they're not odd, so they don't fit in both sets. So set A was the 1, 3, 5, 7, 9. Set B was 1, 2, 3, 4. Only ones they have in common are the numbers 1 and 3. So that's our intersection in this particular case. Which makes you feel okay with the word "and" so far. Good. All right. Now we're going to build this up because you're typically not going to see a problem like this. This is a good introduction, and this is a good introduction to get you to understand the intersection. Really, though, we want to kind of ascribe this to our inequalities and see how that relates to them. So we're going to look at one more here. You know, I might need some more room. Do you have any questions on the word "and" in the Venn diagram over here? Okay. We'll look at these two examples first, and then we'll start talking about "and" in combination with this. Look at your first set. X such that X is less than or equal to 5. Hey, can you give me a number in this set? Why 5?
Because it's equal.
Or equals. Great. Okay, I like it. Give me another number.
4.
Good. Give me another number. Give me another number. Okay, give me another number. 1 through 5. Okay, those are several numbers. Very good. What about another number?
-5.
-5. Why negative?
They're all less.
What about -6? Would that work?
Yes.
Sure. How about -1? How about 3.2? 3.23457. Yeah. This includes a whole lot of numbers, doesn't it? Every number you can possibly think of that's less than or equal to 5. That's what that represents. How about this one? Give me some numbers in that set. 3 works because it's equal to. Someone else give me another number. 4. How about another one? 10. How about 10.2? Good. Or anything greater than or equal to 3. Not 2, not 1, not negative, same thing like that. My question is, if you know this set, and you know this set, which we do now, can we talk about this set? talk about that set, where not only do you have this condition, but you also have at the same time this condition. Are there numbers that satisfy both of them? Can you think of them? This was less than or equal to 5, this was greater than or equal to 3. Do you have numbers that satisfy both, less than or equal to 5, and at the same time, x is greater than or equal to 3? What satisfies that?
4.
3, okay, 3 does. 3 does because it's equal to, it's less than 5, definitely, right? And it's greater than or equal to 3. Does 5 satisfy? How about 6?
No.
No, 6 is not less than 5. Even though it's greater than 3, it's not less than 5. You have to have both. How about 3.2? Yeah. In fact, we have the numbers like we have 3, all the way up to 5, including like 3.000001 and 4.99999. All those numbers within that range are included in this. And there is a way that we can represent this on a number line. If you've ever graphed inequalities, you know inequalities are simply graphed in a number line. So let's look at this. If we have x is less than 5, what x is less than 5 represents? Is that all the numbers to the right or all the numbers to the left? Which one? It's a number line, right? And the numbers that are less than 5 are this way. Great. And if we have x is also greater than 3, where's 3 in relation to 5? It's to the right or to the left? So it doesn't have to be like the scale or anything. There's 3. Where are the numbers greater than 3? So notice what we're doing. We're graphing two different inequalities, right? Graphing x is less than or equal to 5. That's this one. We're going to graph x is greater than or equal to 3. That's this way. What I want you to see is, do they have any crossover? Do these things cross over? Do they cross over here? Is this the crossover? Is this the crossover? Is this the crossover? Where they cross over, hey, that was the same idea as our Venn diagrams. You get it? The crossover is the intersection. They're the numbers that are common to both sets. How many understood that right there? Good, okay. So very much like a Venn diagram, instead of having the circles, this is like one big circle. And this is like one big circle. And where they cross over, that is our intersection. So where your lines cross, namely this region right here. That's your intersection. So graphically, this picture is, this expression is this picture right here. It's all the numbers between 3 and 5 inclusive. Now, we do like to draw pictures like this, and you're going to be doing this, drawing these number lines and showing me graphically what numbers we're talking about. However, there's a better way to represent this, and it's called interval notation. We can say, okay, instead of writing my number line every time, there's another way I can show this. Actually, there's two other ways. I'm going to show you both ways. Are you ready to see both ways here? Okay, the first way is by using this information, I can actually create a nicer compound inequality, a double inequality. Just watch carefully, see how I'm doing this, because you might need to do this in a couple problems. If I have both x less than or equal to 5 and x is greater than or equal to 3, would it bother you if I just reverse these things? Does that bother you? Okay, good. So x is less than or equal to 5. I wrote them the same way. Let me reverse these things. So x is greater than or equal to 3, and x is less than or equal to 5. Does that make sense? Just reverse it. Now, I want you to think of something. If x is greater than 3, is that the same thing as 3 is less than x? If x x is bigger than 3, does this say the same thing as that? Okay. You just learned something there. You can flip around an inequality. It's just fine as long as you flip around the sign as well. Okay? You just write it backwards, and that's legal. That's fine to do. So x is greater than or equal to 3 is the same thing as 3 is less than or equal to x. Nothing to do. Okay. Now I want you to notice something. This is kind of cool. You can do this only with the and inequality. We're going to talk about or inequalities in a little while. Can you do this with the or inequality? Everyone shake your head. No. Can you do it with the and? Can you do it with the or? No. But we can put and together. Watch. If if 3 is less than x, and at the same time x is less than 5, look at that. 3 is less than x, but x is also less than 5. I can match those together. 3 less than x less than 5. This can make 3 less than x less than 5. You can do that with an and inequality. 3 is less than x is also less than 5. I match them together. 3 is less than x is less than 5. Let's see if these still represent the same numbers. Watch on the board here real quick, folks. Here we have the numbers like 3, 4, 5, right? Here we have the numbers 3, 4, 5. Here we have the numbers 3, 4, 5. Does that make sense? Here, look at that. Look at what x is between. Doesn't this show you that x is between 3 and 5? 3, 4, 5. Same idea here. This is it. I mean, this is the way that we can represent a nice looking graph like this in this inequality notation. There's one other way that we can represent this. This is even more concise. This is even better. You ready to see it?
Yeah.
The answer is all you ask. Of course it is. Well, unless you're not ready to see the questions, and then of course you can ask questions. But I want you to see that this actually does represent the same numbers as this and this. Everywhere, and if you understand that those represent the same numbers. Yeah, guys over here? Were you with me? Here you go, you're zoning out, weren't you? A little bit, all right, I saw it. They do represent the same numbers. There's one more way that we can represent this. It's called integral notation. Here's how you write integral notation. You use parentheses or these brackets to show this interval. Now, the interval for which these numbers work are between 3 and 5. That's what this says. It says we're going from 3 to 5 inclusive because we have these equal signs. How we can represent that is by using either brackets or parentheses to represent this range of numbers. Here's how you know whether you're going to be using brackets or parentheses. Brackets are used whenever you have the number included. The number included would be like if you have the equals part. Like if I have this, watch on the board. Please watch. Does that include the 3? That's like 3.0000000 forever and then a little 1 at the end, all the way to 5. That does not include the 3. Does that include the 3? If you include the 3, use the brackets. If you include the 5, use the bracket. If you don't include them, i.e. this. That is where you would use parentheses. Does that make sense to you? So if you have the equals part that says I'm including the numbers, I'm going to use this. So our brackets are used for the equals. Our parentheses are used for the strictly. Just less than, just greater than. So in our case, ladies and gentlemen, can you tell me, what am I going to use, my brackets or my parentheses in this case? Definitely, it has the equal sign. This is very much like a closed circle. Can this be, remember the closed circle on your graphs that you were drawing on piecewise functions? Some of you just skipped your piecewise functions, but some not to. The closed circle meant you include the number, right? Then you include it. That's when you used your equal sign, not the set closed. If you didn't have the equal sign, you use open. This is like your open. Do you see the correlation here? Open or not equal to, that's these. Close or equal to, that's these. So in our case, we're going to go from 3 to 5 and put some brackets around it. That's our interval notation in this case. Very kind and concise way to say all the numbers between 3 and 5 inclusive. That's what that says. Okay, it's kind of a big deal. I've just talked a whole bunch about the and about some set notation. How many people understood what we talked about so far? Let's apply this to some inequalities. Firstly, a little review. Do you remember how to solve inequalities? And the answer is, we probably haven't seen inequalities in a while. Let's see if we know how to solve these things. X plus 3 is less than 8. X plus 3 is less than 8. If you want to solve inequalities, guess what? You can solve them almost exactly the same way as you solve equations. Provided you just kind of pretend, don't change the problem, but just kind of pretend that the inequality is an equal sign and do exactly the same stuff. You're going to solve it the same way you did equations. There's only one little hitch in the giddy up here. That's full concern right there, isn't it? There's only one little hitch, is that if you multiply or divide by a negative, you have to do something special like that. Okay, that's right. So everything else works just fine. So can I subtract 3 like I would normally do in an equation?
Yeah.
Absolutely. Do I have to put the sign around?
No.
No, don't do that. That's fine. The only time you would do that is if you multiply or divide by negative. So we're going to subtract 3 like we would normally do with an equation. Don't change anything about this. Just write x less than 5, and you've got it down. Now, of course, this doesn't have an and associated with it yet. It just says x is less than 5. If you're asked to graph x is less than 5 like this, well, here's 5. Are these numbers the ones to the left of 5 or to the right of 5? Which one? Yeah, you know what? This is kind of nice. If you have an inequality and your x is coming first, this kind of points the way you want to graph. Notice how the arrow is kind of pointing to the left side. Do you see that? It's kind of pointing this way. It's like, oh, there's an arrow that way. Do you see that? It's the arrow pointing that way. If your x, please just listen to what I'm saying now though. If your x comes first, now I can flip this thing around, 5 to x. Is it pointing the right way? No. It's pointing the incorrect way. Your x doesn't come first. But if you manipulate it, like I manipulated, let's see. If I were to manipulate this one backwards, it would point the correct way. Your x must come first for you to graph this correctly. So if your x does